The topic of polarity is a little bit easier to wrap your mind around if you understand molecular geometry. A single covalent bond can be polar, such as a carbon bonded to an O, right? O is more electronegative and is going to pull electron density towards it. But in the molecule CO2, which is linear, you have two oxygen atoms that are pulling equally in both directions. Even though CO2 has polar bonds, the overall molecule is nonpolar because the electron density is not congregated on one side of the molecule. To determine whether a molecule, as drawn in a Lewis structure, is polar, you can't simply rely on the flat picture of the two-dimensional Lewis structure. We have to go one step further. Polarity can only be predicted, but the flat picture cannot alone be used to predict the overall shape. The geometry that we predict from the Lewis structure is a lot more helpful to use. This is a molecular geometry representation of water, and you can see that the overall geometry of water is bent. It has its two non-bonding domains oriented on the other side of the molecule, and yes, there's polar bonds because the oxygen is drawing electron density away from the hydrogens, but that causes a net dipole moment for the entire molecule. And you can see with this area in red that all of that electron density has shifted to one side of the molecule. That causes overall polarity. I'm actually going to show you another diagram here, and this is just a very simple diagram of a molecule made up of one atom that's very electronegative and two atoms of the same element that are not as electronegative. Now, these individual bonds are polar. Now, if those dipoles all start to point in the same direction, this is something that you'll get to in physics. They're called vectors. And vectors, when they all point in one direction, nets a vector through addition in that same direction. So if all of your polarities are pointing in one direction to the molecule becomes polar, and if you apply an electric field, the negative side of the molecule would be attracted to the positive side of something else, and the positive side of the molecule would be attracted to the negative side of something else. So you really need to use geometry to be able to analyze polarity. Linear molecules with different electronegativities, polar. Trigonal planar geometry with identical electronegativities, nonpolar, because each one of those atoms is pulling equally at the 120-degree bond angle. Tetrahedral geometry, same atom, nonpolar, because all of those atoms are pulling equally in opposite directions, and there's no net dipole on one side of the molecule. However, a trigonal pyramidal geometry does have polarity, especially if there's a difference in the electronegativity of those atoms, because all of those atoms are pulling their electron density towards the top of the molecule. If you take a tetrahedral arrangement and you start replacing the atom on the outside with other atoms of different electronegativities, then yes, you do start to get polar molecules. So if you add a fluorine atom or a chlorine atom to one side of this tetrahedron, and you have nonpolar bonds such as C connected to H down at the bottom here, that will cause the overall molecule to be polar. Something to remind you about is this very special case where you have a C connected to an H. That bond is always nonpolar. And we talked about that a little bit in the previous mini lecture, but since the electronegativity difference between these two elements, carbon and hydrogen, is so negligible, that bond will never be polar, so that side of the molecule actually doesn't have any dipoles that we really assign to anything. I already took you through some of the simulation and showed you some of the different ways that molecules can be oriented. I would recommend approaching that simulation on your own time and just kind of looking at the geometries of molecules and seeing how that affects the overall polarity. Let's try this practice problem, and let's see if we can assign polarity based on Lewis structures. Take a moment, pause the video, try these, and we'll talk about the answers. Ammonia is polar, and it's the only one out of this list that is polar. It's because of its shape. If we draw its Lewis structure, it's the only molecule that has electron density lopsided on one side of the molecule. It's a trigonal pyramidal arrangement, and the electron density for each one of these dipoles is pulling up towards the nitrogen. So out of all of these, even the octahedral arrangement of SF6, all of those fluorines would be pulling in equal and opposite directions. Same with the trigonal pyramidal structure of BR3 and CH4, which is tetrahedral. Okay, the electron density is aggregating around the more electronegative atom. The nitrogen atom becomes slightly negative, while the hydrogen atoms are going to become slightly positive. Which of these would you classify as nonpolar? Justify your answer. Carbon dioxide is really the only molecule in this set that's polar because it's linear. You draw its Lewis structure, CO2 with two double bonds. Those oxygen atoms are pulling equally in opposite directions. So therefore, based on its shape, its electron density is going to be evenly distributed throughout the molecule, and it's going to be nonpolar. The other molecules have asymmetric shapes. You draw the Lewis structures for SO2 and IF3 and IF5. Each one of those molecules is going to have electron pairs, which is shifting the geometry of the molecule in such a way that it's going to be asymmetrical in some way. A quick review of orbital overlap, right? We say that a covalent bond is formed by the lowering of the potential energy from orbitals overlapping. There can be two s orbitals that overlap directly. We can also have s and p orbitals overlap directly, and sometimes even two p orbitals can collide and overlap directly. Remember that those orbitals are actually three-dimensional waves. There's constructive interference with the overlap at a certain distance between the nuclei. And this causes these head-to-head overlaps or sigma bonds to be much more stable. A quick review of these potential energy diagrams. We did review this earlier, that if you get the nuclei too close together, their potential energy skyrockets, which is very thermodynamically unfavorable. If you separate atoms by an infinitely large distance, their potential energy drops to almost zero. However, if you get them close enough together that the overlap is constructive, there's some kind of balance between the attractive and repulsive forces, then you get a chemical bond. We're going to talk a little bit about why orbitals hybridize in a later mini lecture.